we're continuing the really in-depth or moderately in-depth. There's always more depth you could do on these things. The in-depth saga of this particular function and its value at 2, where we're starting to just barely get into some non-trivial arithmetic done on omega naught in the style of, well, in exact analogy to the regular kind of fast-growing hierarchy. So what did we find? We found that sort of at the outermost layer, we imagined that we could create this, find this number n, and pretend that we understood this number n, which was a pretty darn high level phi naught function with specifically this expanded out control argument. And well, that plus 1, and that means that gets repeated 2 times. And so we sort of pretending we understood that n, which is pretty ludicrous. And then the last thing that's going to happen is that you're going to apply phi naught of that same argument n times to n. And we've talked about how many things are kind of amazingly big here, but let's just focus on the very last stage. So even if we think n is within our grasp and alpha is maybe not too complicated, which it's not as complicated as these things get, certainly. So let's see. We are assuming we understand the phi naught function with the control argument alpha first with input 2. That's just this guy, which is already going to be pretty huge. And then with input phi naught of alpha 2, the output we just got, and that's going to be n itself. Already that is so much farther beyond the previous numbers we've had in this new series. And then our final answer is we take that number as the iteration exponent on the phi naught alpha function again with input n. So we're using phi naught alpha an incredible number of times, but I want to just focus on the last time. So suppose we're really ambitious and we think, okay, you know what? It actually, we devote, millennia of our lives to understanding phi naught of alpha with that alpha control argument applied n minus 1 times to n. And we're almost on the verge and we're like, it can't get that much bigger. We're just going to plug it into phi naught alpha one more time. And so we're going to call this penultimate stage m, and then we're going to plug it into phi naught of alpha. But wait, what's that going to do? Okay, so this is what we're trying to calculate. We've now got it down to something that looks very manageable, just phi naught of alpha m, no iteration, anything like that. But remember, alpha has still a lot of structure to it, and it's got a lot of omega naughts. It's got a lot of omega naughts times 2 to the omega naught type stuff. And then I'm going to plug m into it. So again, we're imagining m is understandable, but we really have to remember how incredibly huge it is. And then what does that do? It re-erodes alpha just a little bit to this ending with an omega naught times 2 plus the success plus m successors. Okay. And the erosion expansion process that we saw before, that's going to happen on this, but only after we eat through all of those m successors. And so we're going to repeat this with an m minus 1 and repeat m minus 2, m minus 3 unbelievably many times. That's before we even get to the kind of erosion expansion process we had before. And when we do that, when we've exhausted all the explicit m successors that we've got right here, each one of those so far unevaluated omega naughts is waiting there to receive the new huge number. And then we're going to get more omega naughts spitting out of this, and they're going to be receiving the new huge number. And it's all starting with m, which was already pretty huge. So I like to think about those unevaluated omega naughts as these kind of, hidden explosives that the bomb squad is trying to find. And they're all hiding there, and the later they get evaluated, the more powerful they are, because they're just a receptacle for whatever number comes along, and those numbers are only getting bigger as you go. Okay. Whew. So that's about what I want to say about that particular number. Little bit more. Let's see. The initial portion was a lot of these consecutive erosion steps. Yeah, that was such a tiny such a tiny part of the real power, because it's just the power just at every step, it just keeps building on itself and building on itself. But it gives some sort of a feel for what stage you're at. And it was actually kind of manageable. Well, we wrote out a good bit. So, right, where was that? That was this kind of expansion. This was the initial expansion. The first time we got to a successor, and then it started eroding, and then I showed you that sort of what I was calling alpha and beta and gamma, and the stuff that goes into this iterated tower of iteration exponents. And then this was that next erosion process, sort of that structure getting gradually eaten away. Doesn't relentlessly get smaller on the page, but eventually it erodes down to just really to nothing eventually, but it takes an immense number of steps. So that's not something that's absolutely unimaginably huge. That feels like we're making some progress as we write down a couple pages of that. So that initial portion is something that's a little bit understandable and gives you some vague shadow of how powerful it is. And this, if you watch the other videos I had toward the end of the series, I was talking about the F function and the G function and the fast-growing hierarchy and the slow-growing hierarchy. And that kind of relates to this idea of just looking in that initial expansion to get a sense of just where are we. But it's such a pale shadow of what really goes on. Because what really goes on is once you do that expansion and you build this, build this incredible tower of iterations, and then you start having that build on itself, and you kind of come out of those indents over and over and over again. And as I pointed out, even at the last stage, when you think you're almost done, and you come down to just one more, just measly phi naught alpha. Well, alpha is still huge, and you're almost back to square one. You gotta say, this is almost as big as what we started with. It still has this immense structure, and you're gonna put in this incredible m into it. Okay. So what happens, of course, if we put in n greater than 2? Then it's going to be so much bigger. Even the initial expansion is going to be a lot larger. So where are we? And if you know some of the other ways of doing these big numbers. So if you know the Goodstein function, or the standard way to express this level, it's just slight differences. This is the f sub epsilon naught function. And I talked a lot about this in various ways in the other series, because this is where you start to get really interesting connections to proof theory and famous results about what you can or cannot prove with various very stripped down systems of arithmetic and logic and proof. So we are at the Goodstein sequence, Goodstein function level now. So let's go a little further. What about if you just add 1 to this guy? That's always something you want to think about. This was very powerful, and it didn't have any successors built into it on the outside. What happens if you actually put a successor onto that? Let's put in 3 here instead of 2, just to kind of get a sense of how powerful it is. That, of course, means that you just strip off that plus 1. You go back to the control argument we were just looking at, put in a 3 just for fun, 1 more than we did before, and then do that function, and then do it again with the same control argument, and then do it 1 more time. So let's call this n, this last function here. So this is a new n. Assume that we have some idea of that, even though it's the next thing beyond what we had just looked at. Let's assume temporarily that is something we can kind of comprehend. So what are we going to do? We're going to be using doing that same kind of structure, the phi1 of 3 omega naught level, on this n, we're going to do that whole erosion expansion thing. We're going to do n of those steps. Then we're going to do the build towers and towers and towers of iteration exponent upon iteration exponents. We're going to feed back in again and again and again. We're going to get that result, which is this guy. And then we'll take that and we'll put it back into this super powerful gadget. Okay. Now, those initial erosion expansion steps, even if you only pay attention to that faint shadow of the power of the thing, what I was calling alpha, beta, gamma, delta, etc., those alone are based on this that's not just n, but is a phi1-3 version of n. Wow. Okay. And that is just adding 1. Oops, forgot to accidentally erase those guys. Okay. So whenever you've got one of these super powerful control exponents, once you add 1, it's just the super easy way of supercharging that. And then put in, even if you put in a 3, it's a significant supercharge. Of course, if you put in 100, it would be pretty big. Okay, so that's the point I was making, is that's this combination of successors and functions. That's the real power for creating huge numbers. So what's next after this? Okay, we could look in depth at just the next integer here, phi1 of 4 comma omega naught. We do this higher arithmetic on omega naught at the level of creating new functions. It's essentially a triple up arrow level of arithmetic on omega naught, and then we create that control argument and we put in n's like 2, 3, 4, 100, 1,000, whatever. That would absolutely create vastly larger numbers, and we could just spend hours and hours unpacking that and scratching the barest little bit of the surface of the complexity of what you get out of that. But it is time to skip something. Let's jump to a little bit of more diagonalization. Okay, so we're going to put in an omega naught in the innermost control slot. So far, the only things we've been putting in the control slot of phi1 have just been finite numbers. The next thing is to put in an omega naught, because after all, in phi naught, the kinds of things we've been putting in as control in the control slot for that for quite a while have been function type objects. Now, this is not going to be the most powerful kind of diagonalization. This is not something where this slot eats the second slot that I was alluding to before. We will get there, but we're not quite ready. Instead, this is an omega naught. It does eat stuff, but it eats integers. So it certainly can't eat that. That's too complicated. So what's the definition of this going to be? It's really not that hard. We're going to define phi1 of omega naught alpha, where alpha is any kind of gadget, or any kind of gadget in omega 1. That's the gadgets we've seen so far. And we're going to say, okay, this should be some sort of function. Almost everything here is a function, unless it's obviously should be a successor. And the nth stage of that, what happens when you put input n, is you just feed that n into the control slot. So it's rather like the definition of iteration when the iteration exponent was a function. It's just something that's waiting to an integer to get fed into it. So it's really going to be something that collates together all of the phi1 n dot functions. So all the things we've been dealing with for the last few videos, where that's 0 and 1 and 2 and 3 and 4 and 5 and 10 and 100, it's going to collate those together. Now, why am I calling this a diagonalization? I'm not putting this into this. Oh, but when we put that into phi naught, we do get a diagonalization trick, because now the n input, the actual integer input that makes this a function of on integers, that now has a place to go in this slot, and now it goes into the more powerful slot here. It doesn't go into this omega naught, it goes into this guy. And so now as n ratchets up, as I do this 2, 3, 4, 5, 10, etc., it's going to ratchet up here. So that's what I have here. So for example, if I put a 5 into here, now it's automatically going to be, you do 5 level phi1 stuff on omega. So that's I guess a quadruple up arrow kind of Knuth arrow manipulation of omega naught. That's going to create this incredibly rich structure in terms of omega naught, which will unpack in incredibly huge ways. And those will all, as it unpacks, those are all control arguments for phi naught, and it's just going to be insane. Okay. I feel like it doesn't feel like a complete qualitatively, because it's like, okay, well, we could have just done more videos on 4 and 5 and 6 and 7, and then this is just, okay, diagonalized in kind of the simplest possible way over that. And I mentioned that previously when we were looking at just f of omega comma n being f of n. It doesn't feel like it's just absolutely like, oh my god, I can't believe that. And that's because we didn't, and what happened was we combined it with a successor. So let's just see briefly what happens when we combine the successor. I'm going to show you in 2 ways. One is the absolute most simple, which is take this newly powerful gadget, which is designed to have a diagonalization slot in a new way, and then just take the successor of that, and then apply it to, let's say. And of course, what does that do? It just says, let's take phi naught of this gadget, comma 2, which immediately goes down to this guy. Okay, this is, let's call it n, my sort of generic name for a big number. This is something we actually had. It was a while back. It was a pretty darn big number then, but it maybe isn't seeming so big now. But let's remember, it's a pretty darn big number. And then, of course, the next stage is that gets put in as the control argument in this guy. So this is where we had seen, even when this is 2 or 3 or 4, it's just bewilderingly complex. And then we were just putting 2, 3, or 4 into this argument. Now I'm putting this incredibly big number n into both of those slots. And so great example of how we just do the tiniest little bit more than just this guy. We do a little successor. I put in a measly 2. Pretty good. Okay. So this allows us then to have an automatic way of taking big numbers that are the results of these calculations and recycling them into the control input on the top level, the phi 1 level. What's the next value? That's going to be start out with phi naught with this new gadget of 3. That diagonalizes, that's this guy. And then that's going to, let's call that m, much bigger than what we had as the n that was going into the input here, because we've got 3s. Then that diagonalizes into this slot. So now that's being used as the control argument as a way to build omega naught level gadgets. Then we take that and actually implement it with input m. Let's call that L. And then that goes into the powerful control slot of a phi 1. Now we're building this gadget that is unbelievably complicated based on omega naught, and then that's used to control our last phi naught application. So we're recursively ratcheting up the chain of arithmetic on omega naught in just this incredibly powerful way. But what could we do? There's another thing we could do. We could apply the successor on the inside. You always want to think, and you don't want to jump to it necessarily, but you want to think, well, what's the most powerful thing I can ratchet up? This is the most powerful thing. It's the control exponent, inside the thing that controls the control exponent of phi naught. So what is that going to do? Okay, so that takes this new, very powerful, flexible gadget, and it says, do that omega naught times on omega naught, and then eventually put in an n. Okay, now what diagonalizes first? The key is that this is some function. It is a well-defined function, and I'm iterating it a function number of times. That's the thing that needs to get evaluated first. So the diagonalization preferentially goes into here first. So what is that going to do even at the 2 level, for example? It's going to unpack as our new function squared applied twice on omega naught. So I just unpack that out. Okay. And now where is the 2 going to go? So it's when you get a lot of these levels, you got to sort of really look at it like, okay, what's going on here? Oh, okay. It's got this first slot that's got an omega naught. That's ready to eat the 2. This is in the second slot of that phi 1 function. So it's not ready to do any diagonalization. It's going to be this guy. So that's going to be phi 1, 2 of phi 1 omega naught omega naught. Okay, that's a bit of a demotion, because I only am using the number 2 here. But it's still not trivial, right? We know another way to write that is take this new powerful gadget, phi 1 of omega naught, times 2 to itself. Okay, now it switches to where the diagonalization is going to happen in the exponent slot. And when I feed the 2 into here, where does it go? It feeds into the first slot, that omega naught. And that's going to be another phi 1 of 2 omega naught. Okay. So some of this stuff is becoming pretty pedestrian by our current standards. This is just now omega naught times 2 to the omega naught, all in an exponent. The principle, again, is that you go for the highest exponent here. You're going to feed that 2 to the omega naught just becomes 2 to the 2, which is 4. So this overall exponent is omega naught 4. And then that collapses down to an omega naught 3 plus 2. Then rules of exponents, you have times 4. This should look familiar. I'm going to kind of just go through the next. Ooh, and it's getting kind of big. Let's see. Going to have to scale down a little bit more. Oh, maybe not so much more. Okay. I don't want to scale it down any more than that. It's not going to be readable. And so I've got these dot, dot, dots here. What are we going to get here? Okay. Inside the control argument, we're going to get, it's going to start expanding. But notice, instead of omega naughts as the base, it's all of these things that are omega, phi 1 of omega naught omega naught. And then at the last stage, when that starts, when that shows up unprotected, it's going to get the 2 again in this omega naught slot. That's going to be a 2. Finally, oh, okay, that's fairly ordinary arithmetic on omega naught. And it turns out to just collapse down to an omega naught 3 plus 2. But remember that alpha we had in that really big expansion? That was all based on a similar kind of arithmetic where these were all just omega naughts. Now they are diagonalizable arithmetic done on omega naughts, all waiting to do that arithmetic to create massive, massive, massive expansions. So it's structurally similar to that calculation we started with that was at this level, but these unevaluated bombs are now phi 1 of omega naughts, and they turn into really, really big expressions. Okay, let's cut that off here, and then we'll keep going and eventually get to an even more powerful kind of diagonalization than this.